Okay, in this video I'm going to be introducing a part of Chapter 16 and I'll be continuing on Chapter 16 theory in class on probably Wednesday. We'll talk about the schedule in just a little while. Okay, but Chapter 16 is called Planar Kinematics of a Rigid Body, and what we're doing is we're starting over. The four chapters that we've already covered were kinematics of a particle, kinetics of a particle, work energy of a particle, and impulse momentum of a particle. That's four chapters, 12, 13, 14, and 15. Now we're going to repeat those basic topics: kinematics, kinetics, work and energy, and impulse and momentum. But instead of doing kinematics of a particle, now we're going to be doing kinematics of a rigid body. And of course, a rigid body is a collection of particles that behave a certain way. And in going to a rigid body, we're going to recognize that we not only have motion variables that tell us where particles on the rigid body would be located, and those motion variables, velocities, accelerations, they pertain to particular points on a body. But there are also some bodies related, body information related to rotation, which pertain to the entire body. Okay, and we could say that the entire body has undergone a change in angle theta. Now, different points on the bodies would be at different locations, theta, but an entire body rotating would undergo a change in theta. Okay, if we talk about the rate at which theta is changing, that would be a theta dot quantity, or d theta dt, which we will give the name omega for angular velocity. Angular velocity is a property of the body, not just a single point on the body. And then, of course, if we want to work backwards from omega angular velocity, we can recognize that omega dot, which is d omega dt, we will often call alpha, which stands for angular acceleration. So angular acceleration is d omega dt, which is omega dot, which is theta double dot. Okay. Now, so we have two definitions very similar to what we had on the upper left-hand corner of the equation sheet, but involving rotational variables. And just as we did with the linear variables, acceleration, velocity, and position, we can say that angular acceleration is d omega dt, but that's d omega d theta dt, and d omega d theta we'll deal with in just a moment, but d theta dt is omega. And if we move the d theta all the way to the other side, we'll have alpha d theta equal omega d omega. Rather than saying that, because that's sort of a tongue full for me, I'll say the rotational version of a ds equal v dv. And you remember those formulas, I suspect. Let's pop over to the equation sheet, and you will remember the upper left-hand corner of the equation sheet, and you will remember which gave us relationships between positions, velocities, accelerations, and time. And then we had the constant acceleration portion of the equation sheet. If we then jump to the other side, we will see if I can get this into the picture, the rotational versions of the upper left-hand corner of the equation sheet: omega equal d theta dt, alpha equal d omega dt, and a d theta equal omega d omega. Then we also have the constant acceleration versions of those equations. This would be the angular position equation written in terms of angular velocity, acceleration, and time. This would be the angular velocity equation written in terms of angular acceleration and time. And this would be the ADS equal VDV form of the rotational equation. Okay, so the first problems in Chapter 16 and the problems that you're working on right now mostly involve applications of these equations, possibly applications of these equations for objects that are in a very special configuration that we'll talk about for just a minute. Let's get this out of the way. Okay, and coming back to the notes, okay, what we're going to talk about first of all is an object that is pinned to ground somewhere, okay, and that object is rotating about this fixed point, and what we want to do is talk about some of the motion properties of this object. Let's see, let me remember what's on the next page to be able to talk about that. And we can look at this in 2 dimensions, or we're going to look at the same thing in 3 dimensions. And from the physics that you've had, I think you would remember that if we do have an object that's pinned to ground but free to rotate, and if we have a particular point on that object, we can say that the velocity of this point rotating about a fixed point is v equal r times omega. And this is a pure planar version of this problem. We'll need to talk about the 3D version just a little bit more in class when I can talk about right-hand rules and actually demonstrate some right-hand rule stuff. But for now, when an object is pinned to ground and the object is rotating at some speed omega, the velocity of any point on the object is v equal r omega. And of course, the larger r is, the larger the velocity. So the further we move out, the larger the velocity. And of course, the bigger the omega, the larger the velocity. We could also talk about acceleration of an object that's pinned to ground, and that object will have 2 pieces, a tangential piece, tangent to the path, of magnitude r times alpha, and a inward piece in the normal direction of r omega squared. Now we could go back to the equation sheet and remember some of these equations, bringing in the cylindrical coordinates. If we are rotating about a center point, and here's our velocity equation, and if we're at a fixed point on the object, then r dot would be 0. That point's not moving. If we're on a fixed point on a rigid body, r dot 0, because we're not getting closer to or further from the center. And so our only velocity term in cylindrical coordinates would be the r omega term, acting in the theta direction, which would also be the tangent direction in this case. Okay, the acceleration, if r is not growing, if we're talking about a fixed point on a body, all r and r dot terms are gone, so this one's gone. This is the r omega squared term pointing inward, and we have the r alpha term in the theta direction, and this Coriolis term we talked about earlier, which would require a growing r value, or r dot. That term is 0. Let's get this out of the way. And so again, see that we have 2 acceleration terms, r omega squared inward, which is r theta dot squared, and r theta double dot, or r alpha, in the tangent direction. That would allow us to work problems purely planar, in which we have a rigid body pivoting about a fixed point. Now, if we look at some of the same things, though, but we look at it from a 3D point of view, we're still talking about an object rotating about a fixed point, and we're still talking about an object that has planar geometry, and the object is rotating in its own plane. But we will look at this in 3 dimensions. Then we will say that, first of all, this object has a rotation vector which is perpendicular, which passes through the point, which is perpendicular to the plane in which the rotation is happening in. So we would say that our rotation vector omega would be an omega in the z direction only if the end plane would be x and y directions. So this would be an omega in the k direction on both of these pictures. So we have a fixed point on an object rotating in a plane. The object is described in the plane. And we can have, for velocity, a theta dot piece, r is constant, giving us a velocity. And that velocity in pure planar we said was omega times r. But in 3 dimensions, to be very precise about it, we would say that the velocity is omega cross r. I'll be talking about the definitions of the cross products and why those make sense a little bit later. And we will also say that our acceleration in the tangent direction is alpha cross r. And we'll say that the acceleration piece in the radial direction is an omega cross r. Now this does have an r and 2 omegas in it, giving us an r omega squared term. This has an r and an alpha in it, giving an r alpha term. That has an r and an omega in it, giving an r omega term. So it is sort of hanging together. Again, when I get to class and we'll be able to do right-hand rule images, we'll talk about why these make sense in greater particularity. In the next half of the chapter, we will all of a sudden go to general planar motion, in which there is no object that we would say is fixed, that we're rotating about, and we'll start bringing in the relative motion equations, but we're not going to do that for now. What I want to do is look at a few problems that are similar to what you're working on for homework to help get you ready for the homework. And so I'm going to move that out of the way and that. I haven't studied this problem carefully, but let me move it into the zone. Having a little trouble moving it totally into the zone. But okay, there we go. That's a little bit better. That'll work. And let's expand that to be page width size. I can make that a little better. Bear with me. There we go. That's about what I'm after for now. And now I want to zoom in a little bit on the problem statement, and then we'll look at the picture. It says we have a 50 millimeter radius pulley at A of a clothes dryer, rotates at an angular acceleration of alpha of A is 27 theta A to the 1/2 power. So we have an acceleration as a function of theta, and in this equation theta is measured in radians. Determine the angular acceleration when t is equal to 1 second starting from rest. So we're going to have to work in time somehow onto this thing. Let's move this over a bit and take a look at the picture. So first of all, we're not terribly interested in most of what's happening here. We have a motor at point A. It does have a 50 millimeter probably diameter pulley. That one's hard to tell. If we need it, we'll find out more, but we're probably not going to need it. And so what we're given is A of theta, and what we would like to learn is A at a particular time of 1 second. So given A of theta, we're almost certainly going to go to the ADS equal omega d omega form of the equation, and we are. So A d theta omega d omega, but A is 27 theta to the 1/2 power. We make the substitution of this for A, putting in d theta there. As theta goes from 0 to some particular theta, and we'll just call that a generic theta A right now, and omega d omega goes from rest, we were told it started at rest, to some particular omega for pulley A. I say particular, these are just dummy variables for now. And we end up with an omega squared over 2, evaluated between 0 and omega A. And integrating theta to the 1/2 power, we're going to end up with a theta to the 3/2 power. Let's see, phone ringing. I'm going to pause this. Hang on. Okay, I'm back after answering a phone call from my son. And so we're integrating ADS equal VdV in the rotational form, where A was given as a function of theta. And doing that and simplifying, we get that omega is equal to 60 theta to the 3/4 power. That of course involved dealing with the squared term here. We have omega as a function of theta. Given omega as a function of theta, we now have the opportunity of moving into the time domain using omega is d theta dt, and rearranging omega equal theta dt, keeping omega on the theta side, since we know omega as a function of theta here. So we'll be integrating dt on the left-hand side from 0 to a generic t, and we'll be integrating d theta over 6 theta to the 3/4 power, integrating from 0 to a dummy theta. Doing this integral, we'll get a theta to the 1/4 power multiplied by 2/3 over the limit 0 to theta. And we have t from 0 to t, which just gives us t is equal to a function of theta. And in this case, we wanted to find, let's see, what did we want to find? Determine the angular acceleration when t equal 1 second. If we can find theta for t equal 1 second, then we can find that angular acceleration. And so, plugging in the 1 second to the theta, well, we have t as a function of theta after the integration, or we can invert that to get theta as a function of t. Plugging in t equal 1 second gives a theta of 5.06 radians. Now that we know theta, we can go back to our original angular acceleration equation, where angular acceleration was 25 theta to the 1/2 power, or the angular acceleration is 60.8 radians per second. And that takes care of that problem. Let me zoom back out a bit where I can see what we have. I had another problem or so picked out. This one is probably a decent problem. Let's take a look at this one. And let's see, let's expand a little bit bigger to about there. So what we have is two different gears, one with 25 millimeter radius, one with a 100 millimeter radius. And because these gears are able to turn a corner and go at right angles to each other, their shafts aren't parallel to each other. These are called bevel gears. And so we have a pair of bevel gears, and we know something about one, and we want to learn something about the system later. Okay, so we have gear A is in mesh with gear B if A starts from rest and has a constant angular acceleration. So this is the constant angular acceleration problem. Determine the time needed for B to attain an angular velocity of 50 radians per second. So alpha A is 2, and we want omega B is 50. Let's remember which is A and which is B. A is the small one, we know it's alpha. B is the big one, and we want to find, or we know its angular velocity. And so these are both bodies that are pinned to ground, and the rigid body rotates about a certain pin joint. So this one rotates about a line through the center of its gear running horizontal. This gear rotates about a line through the center of this gear, and that line is running vertical, but they're able to communicate at right angles from each other. And let's remember what we were told again. A starts from rest and has a constant angular acceleration alpha. So what we can do is either work purely with A and determine its motion, or we can work with B. We can travel to B, recognizing that, let me point to this one, where these two gears touch, they must share the same velocity, and velocity is tangent to the path of each of these. Where they touch, if they don't slip, they must share the same velocity, and they must share the same tangential portion of the acceleration. Now I'll remind you that any point out here on this large gear has two pieces of acceleration, a tangential piece, which is r alpha, and the inward piece, the normal direction piece, which is negative r omega squared. Where they touch, they must share the same r alpha, and they must share the same r omega, the same velocity. So we're going to use that and say that the r alpha of gear A, where they touch, must be the same as the r alpha of gear B, which allows us to say solve for the angular acceleration of gear B, knowing everything else. So the angular acceleration of gear B is this ratio of radiuses times the angular acceleration of A, and we were told that the angular acceleration of A was a constant 2 radians per second, putting in the 2 right there, and the radius is there. We get the angular acceleration of B is equal to 0.5 radians per second. Now that we know that, we have constant acceleration, we can go to the equation sheet, and since we have constant acceleration and, let's see, determine that, now we want to find time. We have acceleration, time, and omega. We will use the omega equation that involves acceleration and time rather than acceleration and distance. And we want an omega of 50. We started from rest. We have the angular, we have the acceleration piece. This is alpha of point B, or part B is a 0.5 times time, and we solve for a time of 100 seconds. Let's go out and find another interesting problem. Let's see. Those could be, we may be moving beyond what is most interesting. This one would probably be an interesting problem. I haven't read it yet, but it involves integrals, it involves time integrals this time. So let's investigate this problem. Zoom to 150%. That fits. Let's look at the hardware first. This is an automobile starter. In this starter we have gear A driving a gear B, and then gear B is driving a smaller gear which would go out here and interact with a very large gear on the flywheel that would actually start this car. So we're probably in this case most interested in what's happening in the interaction between A and B. Let's read the problem statement. Okay. For a short time, gear A of the automobile starter rotates with an angular acceleration of alpha A is 450 t squared plus 60 radians per second, where t is in seconds. Determine the angular velocity and angular displacement of gear B when t equals 2 seconds starting from rest. The radii of gears A and B are 10 millimeters and 25 respectively. Okay? Or respectively. Maybe even respectfully. And so what we're going to do is we'll take what we know about the acceleration of A, and we'll learn something about omega of A. We're wanting to get the velocity and displacement, and eventually we want to know about gear B. And so we'll get there eventually, but it looks like we're going to stay with A for a little while. And we can always move from A to B using constant velocity or acceleration equations. So the integral d omega is equal to our integral of alpha dt, and so we have alpha as a function of time, which was 450 t squared plus 60 dt, going from 0 to a dummy time, integrating d omega, going from 0 to a dummy omega, which is going to give us an omega a at these limits, which is omega a, and integrating the 450 t squared plus 60, we're going to get 150 t cubed plus 60t, evaluating the limits from 0 to t, which means the 0 drops out, or omega is a function of time. And if we want to, because we were asked what happens at 2 seconds, we could now plug in the 2 seconds and learn omega a at 2 seconds. That's not precisely what we were asking for, but we'll get there eventually. So plugging in 2 seconds for omega a, we get 1320 radians per second at 2 seconds. Now that we know omega a as a function of time, we will integrate that and come up with theta as a function of time. So omega is d theta dt has been rearranged in this form, set up for integral. We know omega as a function of time, and we have d theta on the other side, theta going from 0 to a dummy theta, time going from 0 to a dummy t. Integrating both sides, we get theta here, we get a t to the out of the t to the cubed and t integral, we get a t to the fourth and a t squared term for theta. And then we have theta is equal to a function of time, which involves a t to the fourth term and t to the second term. Plugging in time equal 2 seconds, we then get a theta a of 720 radians per second. But that's the a side. We know the omega and the theta, but we don't know the v side. But we do know the v of the common point between the a and the b gears would be r omega for each of them. So omega a RA is equal to omega a RB. Solving this one for omega b is equal to omega a times RA over RB. So this would be our speed ratio for 2 gears. And the omega of a was 1320. Plugging in the gear radiuses, we get an omega for gear B, moving slower as we expected, of 528 radians per second. And the same kind of thing is true if we integrate the r omega. We would get an r theta, so the arc angle traveled would be an r theta term, and so r theta for each gear is a constant. So we had RA theta A, bring the RB to the other side, we'd have an RB theta B. Those are both set equal to each other. We calculated theta A earlier as 720 radians per, it's 720 radians for theta. And having the ratio of the gear ratios, we get that gear B travels through an arc of 288 radians. That takes care of that problem. Let's see, I think there was one other I think the real one I wanted to talk about is your final one for homework. Okay, in which we have a rotation about this axis, and knowing points on this axis, we could write that as an omega multiplying by a unit vector pointing in this direction, and then we could take any point that we're interested in and develop an r vector from the center of this plate, from the origin, and then rather than doing v equal r omega, we would say that v is equal to omega cross r, doing a cross product. And so I'm going to leave it to you to try this problem first, but recognize you're going to have to do it as a cross product rather than just a simple multiply. And I will remind you of the right-hand rule nature of cross products, and we will talk about that in class on Monday. And that will end this video.